And let me begin by thanking the organizers for the wonderful conference they put together. So, the detection of gravitational waves has opened a new window on our universe, and through that window we can probe things that we could never probe before. For example, general relativity in the strong field regime. We can also probe properties of black holes. We can attempt to distinguish between general relativity and its extensions. We can probe strongly coupled nuclear matter away from Rick. And the opportunity to contribute to the extraction of the new physics, or of the physics encoded in the gravitational waves, gave us motivation to sharpen our theoretical tools and search for new symmetries, search for new structure within perturbation theory, search for new techniques, search for analytic continuations between regimes that we otherwise never thought about. Future detectors will be a lot more precise than the current ones by about 2 orders of magnitude. And because of that, we need to supply a commensurate increase in precision for theoretical predictions. Space-based detectors will have long-time signals, and for that we also need more precision, if only to make sure that precision doesn't degrade over such long times. It's a little unclear exactly what these 2 orders of magnitude translate into orders in perturbation theory, but by and large, and as a rule of thumb, we can start with a couple more orders. All right, a couple more orders. Now, nominally, numerical relativity provides us with the truth at the moment. However, that truth happens to be very expensive and very slow to extract. So we need approximations to make all of that fast. There are several approximations on the market. There are several approximations. The weak field non-relativistic expansion, the weak field relativistic expansion, the small mass ratio expansion, or the gravitational cell force, and all of these take care of the in-spiral part of a merger. And then we have more on the other side of the merger. And all of these are put together in the effective one-body theory, which consolidates available results and give us basically this. And Alessandra will tell us a lot more about this than I can possibly do. Now, most of the amplitudes and quantum field theory effort in the last few years is focused on the Post-Minkowskian expansion. So why is that? Well, one reason is because the Post-Minkowskian expansion is the right expansion when we worry about eccentric orbits and also about hyperbolic orbits. And that should be at some level good enough to proceed. But scattering in general, which is governed by the Post-Minkowskian expansion, is also a clean environment where we can try to address many theoretical subtleties, such as how do we define asymptotic states, about asymptotic symmetries, and so on. Because we have, in principle, we have exact functions of velocity, it allows us to start to explore the structure of perturbation theory. It also provides information for semi-analytic approaches by providing, for example, the basis of functions that can be used to fit numerical data. It is also a path towards strong field gravity, at least in principle, via various kinds of resummation. And last but not least, as we heard recently from Zihan's talk, there is hope that they can yield generic bound observables, including waveforms. With that in mind, here's a plan. The plan is to, after a little bit of break, discuss the milestones obtained via quantum field theory approaches regarding spinless, spinning, and radiation processes. Then discuss the theoretical structures and connections that have emerged from these studies, and also the tools that have been developed to help us with calculations. And especially these tools will hopefully help us with the next calculations. So the ball goes around. So now I should say amplitudes don't come into vacuum. And there was life before amplitudes. There are plenty of results obtained in post-Newtonian theory, which I will not review. But all of this helps us enormously in making sure that what we do with our newfangled techniques actually are on the right track. So there are many techniques. Looks more or less like London Underground. And for each of them, there are various ways for getting from the beginning to some observable. And ultimately, every one of these steps requires some attention. However, all of them have something in common. And that is that they use, at some level or another, particle physics technology, which has been developed over many years for the purpose of particle physics applications. So that includes various flavors of unitarity method, double copy to deal with gravity, also in various flavors, effective field theory methods, integration methods, which turns out to be the bottleneck in the current enterprises, phase space integration, and so on. In all these calculations, the classical limit implemented in the form of Born correspondence principle helps tremendously. Julia talked a little bit about those, about the various types of classical limits. So let me not spend any time on that. So before getting to milestones, it's probably a good idea to talk a little bit about the general features of post-Minkowskian perturbation theory. As Mikhail was describing early in the week, it turns out that post-Minkowskian perturbation theory is organized in powers of the symmetric mass ratio, and it has a very simple structure, which was ultimately understood both from a general relativity perspective as well as from field theory perspective. So it's basically a polynomial with the highest degree given by the integer part of the half of the number of loops. So minus. So first two orders have none of this. Next two orders have one power, and so on and so on. More features, as it happens, at least in the conservative sector, post-Minkowskian perturbation theory has a rather poor high energy limit. The first time where this feature appears, in fact, turns out to be fixed by inclusion of radiation. However, as one goes further down, this doesn't happen anymore. There are mass singularities, and this one takes masses to zero. But that's okay. We are in the classical limit, even though in the quantum theory there are no such mass singularities. But in the classical limit, they can appear. Three loops, or fourth post-Minkowskian order, marks some new features that appear. For example, the non-local in time effects related to the tails, the appearance of elliptic integrals in various observables. However, there is a silver lining here. There is still some clean separation between conservative and dissipative parts. As we go to the next order marks the appearance of the first Calabi-Yau threefold integral in an observable. And it also marks the breakdown of the point particle approximation in the Compton amplitude, whose finiteness requires the introduction of tidal operators, and that leads to renormalization of loop flow, and so on and so forth, that was mentioned in a number of talks earlier. As we proceed to the next order, this renormalization mixes with in the matter-matter scattering and other scattering observables. So, and perhaps there are other features here that will emerge once we actually start thinking seriously about that high post-Minkowskian order. Of course, as Mikhail talked about earlier, and many others, background field calculations for self-force expansion resums this little chart vertically, with the first column being given by the geodesic motion in Schwarzschild or Kerr, or whatever other spacetime we might care for, and then one SF and two SF corrections. All right, so having said all this, the milestones, there are quite a bit of them, and I'm referring to them as milestones as opposed to state-of-the-art because, well, there were puzzles in the past, and I would qualify as milestones something that brings more clarity to that puzzle, even if it doesn't completely solve it. So let's start with one of those, and that requires that I say at least a couple of words about the fourth post-Minkowskian order Hamiltonian. Its form is fixed. These are the coefficients Cn that appear. They are remarkably simple. They are given by, some of this appeared in Benjamin's talk yesterday. We have elliptic integrals, we have polylogs, but there's not It's nothing terribly fancy. The best thing that we need to remember is that, well, there are several of them actually. It's remarkably compact, and it agrees with post-Newtonian calculations. It's been checked from various points of view. Dissipative contributions have been added, or if you wish, computed together with these from other perspectives, not from scattering amplitudes perspective. The tail effect causes difficulties with connecting this Hamiltonian to which is for hyperbolic motion. It causes difficulties connecting it with bound motion. However, there has been recent progress, and there is even more progress that was reported yesterday in the House. So the progress that is mentioned here is, in a sense, a very practical one. The idea is to strip off the bad guys, analytically continue the rest, and supply back the bad guys straight back into straight in the bound motion form, where they can also be computed with relative ease and independently. All right. So what's the puzzle? So the puzzle is related to the symmetric mass ratio dependence. As I was mentioning, it was understood that to this order, it should look something like this. Explicit effective field theory post-Newtonian calculations of the conservative angle produce an extra power of nu. If radiation is added, there is nu square added to both of them. However, the 1 and nu agree. The nu square is just different. So that was the puzzle for a few years. These calculations have been repeated, and the puzzle changed a little bit, but it hasn't been completely resolved. It's in this table. So quantum field theory approach reproduces GR calculations, GR expectations as far as nu square is concerned, and it also reproduces the multipolar post-Minkowskian waveform. And the other two calculations, which are distinct and use different formulas, reproduce either one or the other. There have been suggestions how to resolve this, this difference, but the puzzle still remains. The suggestions are that perhaps there is something related to the frame or with asymptotic symmetry with the asymptotic frame. And another suggestion is that the multiples defined used here are different from the multiples used in MPM. Regardless, and it's of course important to keep an eye on this puzzle and aim to actually solve it, though from a quantum field theory perspective we can't. We have to wait for the PN world to produce something. However, the consensus appears to be that the quantum field theory results are correct. All right. So it's time to proceed to the next, well, to higher post-Minkowskian orders. And there the strategy is relatively straightforward to state, less straightforward to carry out. Start with your favorite method, construct your favorite flavor of loop integrand, integrate it, and in the process maybe break a few teeth, grow some white hair, and so on and so forth. And then from the integrated amplitude, obtain observables Hamiltonian. The difficulties at the next order, that is 5 p.m., was emphasized in Benjamin's talk. It has to do with integrals being a little bit unfriendly. They contain 13 propagators, 9 irreducible numerators, and then some propagators are doubled. There is, of course, standard technology, but one has to be very careful to deal with that standard technology because of the complexity of the problem. And of course, results have been obtained, but they all required careful tuning of public codes, as well as the construction of private ones. Now, because of the complexity of the problem, there are several steps that are useful. One is to really embrace this cell force expansion, and one can do this with a straight face because of the different nu dependence, all of these are separately gauge invariant, so they can be computed separately. That's one. And two, learn from simpler theories or from simpler calculations. So a progression could be this one. First, warm up with something like QED, and perhaps carry out the calculation to all orders in nu. That is, and then worry about general relativity at leading order in nu. maybe n equals 8 supergravity, maybe radiative effects, and then proceeds to the whole complicated GR to SF. And Benjamin reported very nice results regarding gravity with at 1SF. So let me, since you already did that, let me comment a little bit about n equals 8 supergravity and the fact that it has remarkable similarities with general relativity in hindsight. So in case you're wondering exactly what I'm showing you here, this expression, this is basically the entire 4-point amplitude. So the first thing that you should say, wow, this is damn simple. This is a for-loop calculation, and yet I'm not telling you what these rational functions are. They're not terribly short, but they're not terribly long either. Now, the first thing that you should marvel at is that how simple it is. And this simplicity, of course, translates into simplicity of observables, and in GR it has also a similar. There's a similar simplicity, though perhaps not as simple as this. The other thing to notice is that amplitudes are a lot simpler than, or this thing is a lot simpler than the integrals that go into it. There have been unexpected cancellations of master integrals with much more complicated functions than dialogues, and this is also what happens in general relativity, as Benjamin told us yesterday. So one might wonder if there are similar simplifications as one goes to the next order in the symmetric mass ratio, and if so, well, if it's possible to figure it out in advance and perhaps use that information to aid with the calculations. So whether that happens or not, the jury is still out, but there is, in principle, cause for cautious optimism, I suppose. So this is the result for QED. This is the result for QED, both at order nu and at order nu square. And the thing to notice is order nu square is not any more complicated than order nu. It exhibits, in this particular example, the same kind of unexpected cancellations. The standard, the natural functions that appear in these expressions are iterated integrals with kernels of this type. It turns out that the only things that survive after everything is put together, they're just dialogues and trilogues. In this particular case, there are no non-local in time pieces. There are no tails. Yes. Not as far as I'm aware. But, so the thing is that, as it happens, the more complicated function, they are not completely absent. They are absent at order epsilon to the 0. They certainly exist at order epsilon. So that suggests that it might not be, unless one finds an expression for this integrand in which is manifestly finite, which I would have thought is largely impossible, then I guess the answer to your question would be no. Right, so this happens to agree with a calculation by Binney and Damour, who translated a known exact circular solution in QED plus matter to from bound motion circular to the scattering framework. The reason this is possible is because QED doesn't have any non-local in time pieces, so the translation is just this. So again, because of these cancellations, there is cause for some cautious optimism, though, of course, there is nothing like an explicit calculation. So before we close this chapter and proceed to the next thing, let's pause for a second and marvel a little bit at the plot that Benjamin showed the other day, and the progression towards the numerical relativity results shown by black dots of the post-Minkowskian calculations here. This progression does not use EO-Beery summation. It would certainly be interesting to have a look at this, just EO-Beery summation of this, now that both conservative and also radiative pieces at 1SF are available. Of course, this would not be the entire answer because 2SF is missing, but a comparison would give indication about at least the numerical importance of the 2SF terms, depending on the point in parameters. Of course, this kind of agreement gives us motivation to complete 2SF 5 p.m. and proceed to the next one. Right. So, having said this, let's have a look at. So this was about, if you wish, inclusive observables. Let's have a look also at point-like observables, like scattering waveforms. This have received a lot of attention over the last couple of years. They are defined from general relativity perspective, like so. It's the limit, it's the coefficient of 1 over r at large R. From an observable-based formalism, it's the expectation value in the final state of the transverse traceless projection of the metric fluctuation. Or from the Borland quantum field theory point of view, it is the one-point function of the same graviton. The next to leading order spinless waveform was eventually computed by several groups with important input from these four guys. Next to leading order waveform with spin was discussed yesterday by Lara, so let me not spend too much time on this. And we have spin-dependent memory at higher orders in spin that was also computed. So after all, so of course it's interesting to compare with general relativity and see whether we are on the right track. So once, that took a while to figure out, and once the dust settled, the conclusion is that the comparison is successful. Everything agrees with everything. General relativity results are available through 2.5 PN and computed by Binidamur and Geralico, and suitably processed, suitably expanded waveform obtained from a KMOC formalism reproduces this to this order. It also, that the soft expansion of that waveform also reproduces the universal soft expansion terms in derived by Sahu and Sen quite a while ago. And of course produces the non-universal terms, but there's nothing to compare with those. Except general relativity calculations, and those also work out just fine. This comparison revealed revealed a couple of interesting subtleties. One of them is that there is a certain scheme dependence that's necessary, or rather there is a certain scheme choice that's necessary in the theory calculation to match the general relativity results. And the other one is that the general relativity results are in the so-called BMS intrinsic frame, in which the asymptotic metric at t equals minus infinity is linearized Schwarzschild, which of course makes sense. We scatter two particles, you put two particles in the vacuum, and you hold them fixed, let them move, then the metric is the metric of two particles that are widely separated at infinity, hence linearized Schwarzschild. And this actually has a certain, has influences in the calculation. And it produces initially a constant shift, the shear at t equals minus infinity, but then also frequency-dependent terms or time-dependent terms that look like these. And it turns out that these are captured by zero-frequency gravitons, the ones that also have been discussed as contributing to the angular. Now, this expression holds to leading order in Newton's constant. Don't be fooled by the same power of g. This is not a typo. The leading order waveform comes with additional g square, so these two are not of the same order. I was mentioning resummation a little earlier, actually quite a bit earlier. These zero energy contributions turn out it's possible to resum them to all orders. resum them to all orders. They are all given by diagrams that look more or less like this. They are all supported on zero energy gravitons here. And these can be shown to give the correct contributions to the angular momentum loss, including contributions from nonlinear memory, at least structurally. We haven't quite computed them explicitly. And it turns out that they also reproduce the classical square translation generators, strengthening the relation between the BMS frame and the zero energy modes that was observed at one. Of course, this agreement, this remarkable agreement, motivates higher-order calculations. Now, of course, the analytic expressions for these waveforms are a little bit difficult to compute. However, we can always resort to numerical calculations, and this is what you find if you carry out a numerical calculation for the leading order and the next to leading order. The leading order was known for quite a while. And in fact, even before that, by Thorne and somebody else. Sorry, I forget. So what you see here is a plot of the cross polarization of the leading order and next to leading order gravitational wave. The cross polarization is the one that messes with the angle between the two Cartesian unit vectors at infinity. The reason I picked this one is because this one happens to be a little bit less noisy, numerical noise, that is. So green here shows a 90-degree angle between the unit vectors, and then red and blue shows an angle larger than 90 degree or smaller than 90. I was saying that, what you see here, these two are a little bit out of sync. This is accidentally and unintentionally. The thing that starts with green because there is nothing there, then there is a scattering. Oh, the scattering happens in this plane that goes through the center of the sphere, and it's parallel to this. So green is nothing happening, and the somewhat static thing at the end, this is just the gravitational wave. Now, I was saying that it's technically challenging to compute these analytically. This is certainly true, but there has been recent progress by Brunello De Angelis. One of them is here. Right. All right. So this is all next to leading order, next to leading order, and higher. The results are few and far between. However, there has been a conjecture, which was quickly thereafter proven, for the all orders universal terms in the soft expansion, and they are these. The proof involves solving the Tucholsky equation, and they turn out to be all given by the probe limit. And there is a very curious and potentially very interesting connection between this solution and Liouville theory, and then it goes two Weber gauge theories with a particular gauge group. It's not clear if this is just formal or there's anything deep in there, but it's certainly a good idea to keep an eye on this. And if anybody is interested in computing the full order g to the fourth waveform, there's stuff to compare with up to 2 p.m. from NPM. All right. This pretty much covers everything that I wanted to say about spinless stuff. Before I proceed, how much more time do I have? Awesome. Thank you. Maybe I can start speaking a little slower. Remember I started? Thank you. Okay, maybe we can meander towards 25. Right. So spin. There has been a lot of work about spin. There has been a lot of prior work about spin too. There are by now maybe about 8 or 9 ways to compute things with spin. Because of the classical limit, we need to worry about higher spin. Here there's a list of 9, give or take. It starts with things produced by our hosts. And then, so these are the minimal 3-point amplitudes, and then there are exponentially soft factors. There is a 4D EFT that's in the classical limit, and so on and so forth. There's input from higher spin gravity and massive higher spin gauge symmetry. And then last but not least, there are background field calculations and extraction of exact or potentially exact amplitudes from the Tucholsky equation. So now it's worth emphasizing that even though we have that many ways of computing things, a large number of them are in fact currently conjectures. In particular, everything that's above the first 7, give or take, they're all conjectures, because ultimately a Kerr black hole is a Kerr black hole, as Vitor was telling us the other day. And these, the first 7, should at some level match what gravity with a Kerr black hole in it produces. And to some order, namely to order spin to the 4th, they do. Here are some interactions that have been given to us by Justin quite a while back. So these are 3-point interactions. They can be used to construct this, if you wish, leading order spin-on-spin scattering. However, despite substantial effort, the principle that determines the higher order interactions of a Kerr black hole remain elusive. There is the minimality assumption that was assumed. There is massive higher spin symmetries that were assumed. There was spin shift symmetry that was assumed. Unfortunately, fortunately or unfortunately, this one seems to be broken beyond spin to the 4th, but appears to survive in the probe limit. So given that it's a little uncertain how to describe a Kerr black hole from first principles in a quantum field theory, I would like to propose, and it's not really my proposal, it has been proposed that, that it's convenient to cast a much wider net. Attempt to describe the most general spinning object, whatever that may mean, and once the first part becomes clear, we can always specialize. So this most general spinning object has been discussed for quite some time. From a PN point of view, this is an action that was proposed. One might want to consider including other effects in here, for example, spin magnitude change, absorption, more spin-related tidal effects if there are any. The list goes on. However, once the list goes on, there is really one set of words that comes to mind, which is higher spin effective field theory. So there is one that I'm particularly fond of. Doesn't look terribly pretty, but it also exposes certain puzzles, if you wish. First is that it appears to be incompatible with the Tucholsky equation starting at spin to the 5th, because this one assumes everything is conservative and the Tucholsky equation includes some absorption. There is a solution to this, include absorption. This was not done in this framework, but it was proposed by these people, many of whom are in here, and this is an action that realizes this. Linearity so here the spin is S, and linearity in S ultimately is telltale of presence of absorption. A second puzzle that appeared from a study of this action is that there are more Wilson coefficients than one might have expected based on previous studies of general objects. The puzzle was what's the physical meaning of these extra Wilson coefficients. They turn out to be related to conservative spin magnitude change. And to see this, it's important to acknowledge that the spin supplementary condition, which ultimately leads to conservation of spin magnitude, can in fact be relaxed. Because the spin is not variable in this action, there are several ways of doing this. I'm not going to describe any of them in detail. The idea, however, is that the violation of spin supplementary condition is parameterized by a vector. Here we call it K. On the next slide, it's going to be called Z. Anyway, there is a vector that parameterizes this, and essentially the previous action doesn't change. The only thing that happens is that it gets slightly reorganized to expose this K. So here's an example. And so the amplitudes are in fact the same. However, the Hamiltonian that's extracted is a little bit different because of the extra degrees of freedom that appear in the scale. It also turns out that for specific values of this extra Wilson coefficients, this vector k actually decouples. So this can be interpreted also as a machine that lets us carry out calculations with a constrained spin without actually imposing the constraint. This has been verified up to some order in spin and in G, together with Hamiltonian and Eikonel formula and so on. I would be remiss if I didn't mention a parallel approach to exactly the same problem due to the Humboldt group, which was also used to recover basically the same up to g observables up to g squared spin to the fourth. There are in fact two formalisms, one which is Hamiltonian, one which is Lagrangian, but by and large the idea is essentially the same. There's a variable called z, which parameterizes the departure from the spin supplementary condition being satisfied, and by imposing that this z doesn't change or that the total change in z is 0, one determines a collection of coefficients for terms that involve z such that this doesn't change, and therefore the spin supplementary condition. Now this vector that departs from the SSC, in fact, if one embraces it and attempts to see if it actually has physical consequences, one concludes that it does. Here's an example of waveform, the dashed line. It does in the following sense. It is not degenerate with the Wilson coefficients. Therefore, there is no way to remove it once it was allowed to appear. So here is the dashed lines are waveforms with k equals 0. And then imagine that we turn on k and attempt to adjust Wilson coefficients to remove it. Here, these are the difference between the dashed lines and this waveform with k is represented by the solid lines. And the Wilson coefficients were fixed so that the memory is as unchanged as possible. Sometimes it's not possible, like here. Sometimes it is. It's in the red case. But anyway, long story short, k appears to affect observables. K also fits, or z again, fits very nicely in Warline descriptions of spin multiple expansions. The original versions involves just the first one, c times s, and k fits right next to it. So from this perspective, k describes additional massless degrees of freedom of certain massive spinning bodies, but at a scale that's a lot lower than the scale that's responsible for the generation of the spinning-induced multiples. The plots that I showed you here involve only spin to the power 2. It turns out that it's an interesting that interesting features appear if one resums all the spin contributions. So here are some bumps and wiggles that appear if one does this resummation and one allows the ratio spin by impact parameter to be fairly large. Of course, nothing happens when this ratio is small. It would be interesting to figure out what if there is a counterpart of this and how does it look like for bound waveforms. Beyond 2 p.m., beyond one loop, the results are relatively few. There has been a confirmation of G cube S square results obtained some time ago by Gustav and the other Gustav. And we are going to hear relatively soon from Alessandra about importing some of this into the there is a lot of work that has been done in the last year or so regarding absorption. Katsuki reviewed some of this yesterday, so assume that everybody paid deep attention and gloss over this. There have been results and a careful study of tidal effects and physics beyond GR, at least in 3 different models: R-cube deformations, scalar, Gauss-Bonnet, and dynamical Chen-Simons theory. There are a number of observables that have been constructed leading order in Newton's constant, all orders in spin, leading order in Newton's constant, and leading order in spin. And as far as tidal effects are concerned, there is a slightly longer than a year ago, but never mind that. It's an interesting result. In general relativity, tidal coefficients are self-generated as one reaches for loops, and therefore, at that stage, there is no way around adding them to the action. But one can attempt to add them earlier and study them. One just has to keep in mind that in the full theory, one has to shift whatever is done here by 4 loop orders, because this e's, they really come with an extra g to the 4th. In any case, this study reveals the expected randomization, also the expected mixing with other tidal operators and so on. Of course, the log numbers that we've heard from Julio and Julia and so on, they will be the values of the renormalized coefficients of certain combinations of these operators. All right, that's basically everything I wanted to say about spin. How much time do I have left? Over 10 minutes. All right, so in the remaining 10 minutes and 10 slides, maybe more, let's talk a little bit about novel theoretical structures that, these 10 minutes, are they really 10 minutes or are they 10 minutes plus questions? All right, thank you. It's great, a great bit of news. All right, so structures. There are, in fact, way too many structures to fit into 10 minutes plus 5. But let me mention a couple of them. So calculation of the next leading order scattering waveform revealed a curious relation between the real contribution to it and also the virtual contribution to it. Basically, the real contribution turns out to be a rotation of the virtual contribution. It's an interesting question if this is an accident or if there is a deeper structure here that goes beyond. There is, again, reason for cautious optimism, because as was shown by these people, there is a natural way to combine this and the rest, essentially by using the Schwinger-Keldysh formulas, and that suggests that this bit, in fact, nicely fits inside the other bit. So it doesn't sound completely crazy that, in fact, they are related. The other observation is another observation. Presumably there is structure there, except that we don't know how to use it. I mentioned it before. Amplitudes are much simpler than integrals. Other non-perturbative structures this time involve resummation, which I discussed. So they are related with to BMS super translations. It's a very interesting question. What about the other BMS transformations? And another interesting question is whether there are other consequences of these of this change in the asymptotic frame. More non-perturbative structures involve the iconal, or more generally the exponentiation of amplitudes, which has appeared a number of times throughout the week. There is a version with spin, and the canonical, it involves the canonical spin, and a particularly strange-looking operator that comes from nowhere in this particular formulation, other than if it works. There's a covariant version, which absorbs this as a particular shift of momenta and spins at lower orders. This is a very neat construction, and it's somewhat similar in spirit with this rotation here, though the direct connection is not totally clear. There is an operatorial exponentiation which goes beyond 4 points, which is used in the first 2 points here. There is exponentiation in terms of n. There is exponentiation in terms of iconal phase and also other creation operators here, C and C dagger. There's also an iconal approach to absorptive processes, which is a little bit more complicated, but it generalizes the n exponentiation in this fashion. This has been used, again, to deal with absorption processes, change in spin because of the the absorption, change in mass because of the absorption. Also, structure has appeared and has emerged from the study of simpler theories. We talked a little bit about QED, so let me gloss over that. There's the scalar model that's a particular favorite of the cell force community, which we studied some time ago to address the question whether it's possible to marry cell force approach and post-Minkowskian approach and extend the validity of both of them. This discussion has been extended by Long, Whitall, and Barak. And the new bit that was included is the behavior of the scattering angle near the critical impact parameter, which marks the separation between unbound orbits and bound orbits. So using this information and using this proportionality, they essentially resummed the scattering angle. And the result is the orange line that overlaps remarkably well with the blue dots, which represent the result of numerical calculation for this value of velocity. The thing that is worth remembering for a little while, or maybe for a longer while actually, is that this improvement is not only in the regime where the post-Minkowskian approach is not valid, namely when the angle is particularly large, but also in the regime where the post-Minkowskian expansion is in fact valid. So this in fact illustrates the power of building analytic structure. This also exposes an interesting puzzle that has been mentioned, at least in private conversations over the week. Our numerical analysis indicates that a certain static log number should take this value. Now, you might notice that the error bar is not particularly tiny, so this is, in fact, consistent with 0 within errors, and the fact that I called it static should indicate that I actually implied that it should be 0. And this value was also suggested by a worldline analysis, and it was mentioned in Leo's and Julia's talk. There is, however, a 1SF analytic calculation which indicates that this coefficient is in fact 1/6. Curiously, 1/6 is also within these error bars, as well as a collection of other numbers between 0 and 0.3.1. But of course, the puzzle is which one is it? The thing that it's worth remembering, seriously? Okay, this doesn't want to go back. The thing that's worth remembering is that this particular, or at least realizing, is that this particular fit, in fact, used C1 equals 1/6. Anyhow, it's a puzzle. It's worth keeping an eye on it and attempting to solve it. In the remaining, I suppose, 5 minutes, give or take. Okay, okay. Oh, okay, that's remarkable. Maybe I can now speak properly. Right, so they say that necessity is the mother of invention. So because we need stuff, we had to come up, or rather, we as a community had to come up with new general purpose and special purpose tools to actually obtain the results that I was describing, and also hopefully produce more results in the next round. So we've learned how to do integrals a little bit better, right? So there have been massive improvements to public codes, and there have been private codes have been constructed, which eventually maybe will become public. There has been a systematic analysis of single-scale integrals and the associated geometries. We saw the first observable that contains a Calabi-Yau space. We also learned how to compute, or at least how to begin thinking in a somewhat systematic way about Fourier transforms of Feynman integrals and Fourier transform like Feynman integrals. There have been generating function for tensor integrals that has been constructed as an alternative to Passarino-Veltman reduction. And last but not least, there has been construction of an approach to a systematic construction of finite basis of finite integrals. There have been new amplitudes and new amplitude methods that have been constructed. We're going to hear from Zvi later today about a nice technique, if I can say so myself, that streamlines cut merging. Basically, it identifies amplitude terms or integrand terms with terms in cuts, and it also allows use of the double copy to loop orders. There has been a new approach to the construction of the iconal that Sungmin told us about, the Magnus expansion, which basically machine that lets us take the logarithm of the time-ordered exponential. There have been new Compton amplitudes that have been constructed with higher spin, including absorption, using insights from higher spin field theory and higher spin gauge symmetry. There have been new Compton amplitudes constructed from classical scattering that they also include absorption effects, and they have been also sewn into loops. There have been new Compton amplitudes constructed from string theory or from a bootstrap type approach. There have been new proposals for new computational methods. The Schwinger-Keldysh formalism as a means to enforce causality. This happens to be equivalent to the observable base formalism, and it manifestly cancels the superclassical or the classically singular pieces, and as well as the acausal terms. There have been quite recently, actually, a model agnostic approach to the observable base formalism for spinning observables. There's K or Z and Wilson coefficients as a means towards the spin supplementary condition. And last but not least, there is synergy with this is me. There is synergy with traditional methods and also with other fields. This is something that we should be very grateful to, because it means that we can learn from the other fields, and the other fields are eager to learn from us. There is the bound to unbound continuation, and again, we learned from Zihan the other day that things might in fact be a lot better than they seem, and there could even be an analytic continuation for waveforms. We're going to hear from Alessandra in an hour or so about EOB and meeting post-Minkowski and theory. And again, the study of simpler models like QED and the scalar model continues to yield insight regarding love numbers, integration, resummation, and whatnot. And last but not least, and as strange as it sounds, some of the results that have been obtained along the way, in particular about QED, they could have a phenomenological application to ultra-peripheral and diffractive scattering in QED, and in particular, actually in heavy iron. So, oddly enough, this brings me to the end of my talk and the end of my time. And oddly enough, on time, I think. So there has been enormous progress in the last year or so, and of course also in previous years, towards meeting the 2 orders of magnitude that I was advocating, following the general relativity community that are needed to extract the physics from future gravitational wave observations. But of course, we're not quite there yet, and in fact, we're quite ways away from there. There is a list of things that basically I talked about all of them, and the reason they are still here is that each of them requires further attention and further development, of course. But the one bit that I would like to emphasize is that we should keep in mind exploiting the feedback that we get from this effort, feedback into amplitudes and other fields. In any case, given the rate of progress, we can expect many more results, both for gravitational physics, for gravitational wave physics, and more generally for understanding gravity. Thank you very much.
Okay, thank you, Radu, for that very nice review. We certainly have a few minutes because you started late for some questions. one in the back.
Thanks, Radu, for interesting talk. So this is more of a comment rather than a question, but since you mentioned that the cut seems to be computing the rotation, uh, actually that can be seen even more cleaner when we're not looking at the scattering waveform, but computing the impulse. And there, the cut has an interpretation that when we go to the iconal slide, there was the iterative part of the iconal. And our understanding is that the iterative part, so the double nested Poisson brackets, are the part that actually computes the cut, and that gives us the longitudinal part of the impulse, which generates the scattering angle rotation of the impact parameter plane. So this was more of a comment rather than a question. Okay.
I'm assuming you're referring to a two-loop calculation here. So I thought I was under the impression that at one loop the cut actually cancels completely.
So let me think. Because that was more like an iconal calculation that we did. So we weren't computing the scattering waveform, we were computing the impulse. And there's this formalism based on Worldline QFT that you can compute the impulse from retarded propagators. And one of the things that we found was that the iconal is computed by the symmetric propagators, and they're going to be different from the retarded propagators. So that difference we can impose as the cut. And when you try to reinterpret what the cut is computing, it actually computes the Poisson bracket between the leading order iconal and the leading order impulse. And that is the part that actually generates the longitudinal part of the impulse or the rotation of the impact parameter plane.
Any other questions?
So quick comment and a question about this disagreement about the C1. There were many previous calculations using static linear response of this coefficient, not only by scattering, by many people, which also gives 0. So it's just that we were not the first ones to calculate it. There's like a long history.
I certainly agree. There was one little paragraph here that the last one here that I inconveniently apparently skipped over. Yeah, that's absolutely fair.
Okay, yeah. And then about these logs, these all-ordered logs in the waveform. So I guess the first few by Sen and friends, these come from kind of leading and subleading soft graviton theorems, if I understand correctly. Do we know what is the, I mean, there's a conjecture for kind of two all orders resumming these logs. These are IR logs. Do we know what principle this is based on? Is there a symmetry? Is there something that tells us about these all orders formula? Yeah.
Not as far as I'm aware of, though there is a paper by Silvia Nagy and collaborators who seem, if I remember correctly, they suggest some sequence of symmetries, basically. Maybe, so the answer is a definite maybe. Since everything is given here by the probe limit, so this is a wild thought. Since everything here is given by these terms are given by the probe limit, they might actually have something to do with the integrability of geodesics.
Another option, because in the partial waves, there's only a single IR log that you can expand to all orders. It's just the usual like 1/r log. So I wonder if it has some connection. Thanks.
Okay, I think we should thank Radu again for that nice talk.